Lecture 12 covers section 4.5. At the end of today's lecture, you should be able to apply mesh current analysis, abbreviated MCA, to circuits with independent voltage sources. To begin, mesh current analysis requires us to construct a mesh, which is a circuit loop that contains no other loops within. That is, it's the simplest KVL loop that we can construct within our circuit. A mesh current is a current that follows our mesh, i.e., it would be the current following our KVL loop. For n meshes, we will construct n KVL equations, and we will use Ohm's law to express the voltage drop within our KVL equations to our mesh currents and the resistors that they flow through. It is noted that mesh current analysis only works for planar circuits. That is, if we have a circuit that has a bridge, i.e. an element overlaid another element, MCA will fail. To begin, let us look at the following circuit. We have a voltage source that feeds into R1, R2, R3, R4, R5, R6, and R7. We can construct mesh currents. That is, we have 4 unique mesh currents within our system. I1 exists around loop 1 that encompasses our voltage source R1 and R2. I2 exists in mesh 2, which encompasses elements R2, R4, and R7. I3 exists in mesh 3, which encompasses elements R3, R4, and R5. And lastly, I4 exists in mesh 4, which encompasses elements R3, R5, and R6. Unlike KVL, we will not bypass any elements. That is, we will not create one large mesh that, say, passes element 4. Rather, we want to construct the simplest meshes such that we can describe the voltage drop of each element within our system. We've seen in the previous example, as well as a circuit on this page, that we can have elements that share mesh currents. That is, R2 has both mesh current 1 and mesh current 2 running through it. That is to say, its voltage drop is going to be dependent upon the numeric value of I1 and I2. We see the R1, R3, and R4 are not shared. That is, R1 carries mesh current I1, and R3 and R4 carry mesh current I2. When we have elements that share mesh currents, we have to create a description of that. For instance, if we look at our current source on the left, where we have mesh current I1 entering the positive terminal of a current source, and mesh I2 entering the negative terminal of our current source, we see that I1 opposes IS, whereas mesh current I2 is in the same direction as IS. Thus, our net current through our current source can be expressed as IS, our output, would be equal to I2 less I1. Now say we have a resistor that shares 2 mesh currents, I1 and I2. If we draw a current I going through a resistor and apply a voltage potential consistent with our passive sign convention, we see that I1 is in the same direction as I, where I2 opposes I. Thus, our net current through a resistor can be expressed as I1 less I2.